my aim is to basically go into deeper into this particular variational Bayesian and to show you. So variational Bayesian, linear regression, logistic regression, what was it shown in this? So how to derive the posteriors? Has it been shown there in the earlier class? Can you please tell me? Can anybody please confirm that whether this linear regression, logistic regression, and all these things were derived in case of variational Bayesian inference or not? Yesterday we did this particular sampling based mechanisms. Okay, so today we are doing this optimization based mechanism. Okay, and this is a this is called as a deterministic approximation of the posteriors. Whereas in the last yesterday's class, what were covered, even this Hamiltonian Monte Carlo, that is also called as stochastic approximation. Now, Hamiltonian Monte Carlo is actually a little bit better than this Markov chain Monte Carlo, because Markov chain Monte Carlo, it is all about randomization. So in Hamiltonian Monte Carlo, actually what happens, that we are giving a direction of that search. Okay, we are giving a direction of that search. So it will be basically kind of some kind of physics informed, and whenever we are having this particular direction based search, so that is basically coming from the gradient. Okay, and gradient is basically dependent upon that what is the function, what is its type, and all these things. So we are actually importing some kind of the problem specific nature. Okay, we are not truly data driven. Okay, we are actually giving some kind of physics based input. Okay, so this is what actually this Hamiltonian Monte Carlo and Markov chain Monte Carlo, that is they are different at. Okay, so just wait 1 or 2 minutes. So is it okay? Are you understanding whatever I am telling? So so today we are on day 3, session 3 now. Okay, so let me just start. So again, I'll be using this slides to write down all these mathematical expressions. So please follow. Actually, yesterday I did a small mistake while computing this particular posterior for this linear regression using give sampling. So have you cross-checked it that I have actually made uh, some change in that particular slides? So let me show you. Show that first. Okay. Okay, so this is yesterday's slides. Are you following me? Are you following me?
Yes, sir.
Okay. Okay. So here you can see in this particular. Okay. Thank you. So in linear regression, basically, if I'm going to this particular give sampling based derivation, so here actually I did a mistake that this one here actually this particular when I'm completing that square. Okay, so if I take this particular expression out of this whole expression, then it will be coming out as it is. Okay, so if I send it in the denominator, then it will be to the power -1. Okay, so it will be to the power -1. Then only it will be going in the numerator. Is it okay? So this was the mistake I did. So that's why I was stuck in this particular point, and nobody actually helped me. So I was expecting some help from you, but you didn't help. Okay, whatever it may be, later I actually found it out that yeah, this was the problem. Is it okay? And after that, we did this. Means all the things were they were okay. Okay, it was not a problem. Okay, so let us go for today's lecture. Let us start variational inference for linear and logistic regression. Uh, so first, what we are going to do, that we are can anybody please confirm that in variational inference, what are the things were covered? Is anybody taking notes? Is anybody taking notes? Can anybody please confirm me that what were the topics in variational inference that were covered? Yeah, Mr. Naveen wants to say something, I think. So let me just do some cold call. Mr. Gaurav Agarwal. Mr. Gaurav Agarwal, are you there? Yes, sir. So tell me, what are what were the topics covered in variational inference in the last session? Can you please name them? That's all. If you can name them.
Hello.
Please.
Yes, sir.
Mr. Gaurav, please.
We talked about Hamiltonian Monte Carlo
But
approach.
that was in the last session, in the first
Okay,
session.
last one you're talking about variational
Last
inference.
variational inference. So what were the topics? Means, yeah, Bayesian probabilistic. Oh, that is okay. We are in probabilistic machine
So
learning.
probabilistic pipeline. Then we talked about how the prediction is done using assumptions on the massive data. How we infer from the patterns.
Okay.
And we have latent variables and we have
Okay. Yeah, latent variables.
then we use the model to uncover those, and then we use Bayes rule to find the uh, posterior
Yeah.
using the prior and evidence. But the evidence is difficult to identify.
Okay.
So we use the other method, probabilistic
Yeah.
machine learning,
Okay.
using that.
So okay. Ms. Sakshi, so can you please tell? You are right. It is deterministic approximation, but it is not in a sampling framework. Yeah. Can you please tell? Please tell something. Okay. It's not that I'll be giving the judgment hand till death. Okay, if you cannot tell anything. Okay, so please tell something. You just tell. Yeah, you have pointed rightly. Means you have actually written it rightly that it is deterministic approximation. It is not sampling.
Deterministic approximation is there is an evidence and target that is px and
Okay.
this and in
Do
this
it.
Gaussian made peak like there's a model in which they
Yes.
have shown like
We are basically approximating
yeah.
the true posterior using some representative distribution.
Right, yes.
Isn't it? That Q is that representative distribution by which we are approximating the true posterior, that is P. So now we are actually finding out that what is the so whenever we are trying to approximate uh, a distribution using another distribution, so there will be some gap. Okay, isn't it? Means suppose if I want to approximate a normal distribution using a gamma distribution, there will be a gap, or a gamma distribution using a normal distribution, there will be a gap. Gap means that what is the approximation error we are doing? That error, right? So we have to quantify that. And KL divergence actually helps us in quantifying that. Isn't it? Am I correct, Sakshi? Okay, so let me ask somebody else. Okay. Okay, so let me start. No issues. So I'll do it here. share screen. Okay, so today is day 3, session 3, and we are starting this particular linear and logistic regression using variational inference. Okay, so but before going into that, we'll be looking at little bit at this particular, that how we did arrive and what is the basically specialty of this variational inference. Acha, so how many of you have heard of these variational encoders, autoencoders? I think many of you. Anand Shankar, you wanted to say something. Mr. Anand? Mr. Anand Shankar, your name just reflected here. Tell something, no issues. Maybe wrong, maybe kind of, you just tell something. Yeah, no, sir. Okay. Okay. So basically, what happens that there are this main objective of, so objective of posterior simulation is to approximate, okay, approximate the approximate the approximate approximate the true posterior distribution, okay, using some representative distribution, using some representative uh, using some representative distribution. Okay, so this is what actually happens, right? Now there can be two main categories of methods. Okay, so one is sampling based mechanism, sampling based mechanisms, methods, okay, and another is optimization based methods. Right? So here in sampling based methods, they are also called as stochastic approximation. They are also called as stochastic approximation. But rejection and importance sampling, they are not that much, means they generally are not categorized in this stochastic approximation, but you can club them. Okay, it is also sampling based methods, right? Now here we saw the rejection, importance, okay, then metropolis, then whole Markov chain Monte Carlo comes into picture. Rejection and importance sampling, they are not generally considered under Markov chain Monte Carlo because of they don't have this particular stochasticity nature. What is stochasticity, by the way? Can anybody tell me what is the difference between stochastic models or stochasticity and randomized models, or randomness? Okay, randomness and stochastic. Okay, can anybody tell me what is the difference? So many a times you'll be finding that they are actually used interchangeably. Can anybody tell me? Okay, so this Markov chain Monte Carlo, yeah, that uses randomness, but how it is different from the simple randomness? Randomness involves stochastic. Okay, okay. But the thing is that how, means why we need this particular term stochastic if randomness can tell everything? Can anybody please tell me? So randomness is basically means uncertainty in the situation. Okay. Now this uncertainty can be of two types. So how many of you have heard these two terms? One is called as cross-sectional data and another is time series data. How many of you know this? Cross-sectional and time series. What is the difference between these two? Cross-sectional data and time series data. So cross-sectional data, it assumes, okay, so let me write it a little bit. So cross-sectional data is basically, it is telling that captured the data, okay, so this is cross-sectional data, captured the data at almost same or nearly same point of time. Okay, so suppose let me give you the example of our census. So census is going to start very soon, right? Now what will happen that it will be running for 1 year around. Okay, so census will run for 1 year around. Now the thing is that many people in this 1 year might die. Many will be born. Okay, many will be having 1 year. You can say age 1 year added. Okay, many of things means many will be who are in adolescence. They'll be by 1 year they'll be you can say lengthier, or you can say their height might increase by suppose 1.5 feet. Sorry, not half feet. Okay, 6 inches might be increased. Okay, getting my point. So what I'm trying to say that here we are assuming that all the in context of use of stochastic is scientific use and for general use randomness. No, I'm coming to that. So basically what is happening, we are actually assuming that all this census data has been collected at the same point of time or nearly same point of time. Okay, because we don't want to you can say include the effect, or we don't want to study the effect that in this 1 year what has changed. We don't want to include that, and that's why basically it will be told that census done in some year, okay, 2025, like this. But in some cases, okay, this dynamicity is over the time, how it is changing. Okay, that is actually very important, like stock market data. Okay, like stock market data. So what happens that in stock market, basically suppose the closing price of any stock, that is of very importance. Okay, so it is of paramount importance. Many people actually look at that, and based on that they try to invest in the on the next day, right? Now the thing is that if you don't consider the trend, or the you can say the dynamical nature of this particular data, that how it is changing over time, so you might be naively then investing. Okay, so it might have anything might happen. Okay, and you have to take that. Okay, so what is happening that in case of cross-sectional data, it is assumed that the data has been captured at almost same point of or nearly same point of time. Okay, acha, in time series data, basically what happens that the time series data, okay, so dynamicity of the data is considered. Dynamicity of the data is considered. So that's why what is happening, Markov chain is actually very good in modeling this particular dynamicity. That over time, how is your choice is changing. Okay, so if I tell you that today you are using suppose the bathing soaps. Okay, so what is your choice? Okay, so over time if I see, then if I look at this particular suppose last 1 year, then you'll be finding that it is suppose Lux, then suppose Dettol, then Lux, then Lux. Okay, in this way it is basically happening. Now the thing is, what is the probability? So suppose three soaps actually generally you are buying 3 soaps only. Okay, you are limited to 3 soaps only. One is Lux, one is Dettol, and another is suppose Lifebuoy. Okay, now you can actually create a transition probability matrix. Okay, that how your choice is getting changed over time. And based on today's data, if you look at suppose after 100 iteration, what will be your choice? Okay, what is the probabilities of your choice? Okay, then you'll be finding that Dettol has got a fixed probability of getting selected. Lux is also having a fixed probability of getting selected, and third one also, Lifebuoy also will be having a fixed probability. It is not changing over time. So what will happen that based on today's transition probability matrix, so if you look at 100 times, suppose 100 iteration in the future, okay, 100 time periods in the future, okay, then what will happen that you'll be finding that the choice probability are not changing over time. They are getting fixed. And that is actually known as stationary distribution. That is known as stationary distribution. So that concept is basically followed in sampling based method, especially in Markov chain Monte Carlo. Especially in Markov chain Monte Carlo, we are actually exploiting the fact that that over time, if we look at many times in the future, means many periods later in the future, okay, then you will be finding that the choice probabilities, okay, or the you can say the transition probability is a fixed matrix. It is getting a you can say fully stable matrix. Okay, it is not changing over time. So this is what it is. So that is the target distribution, and that target distribution is the approximate posterior for the true one in case of sampling based method. Now almost same thing is used, okay, almost same concept is being used in variational inference, but here in a different way. So what is that different way? That suppose I am having this is my true posterior, okay, so that is p theta, okay, and I am actually assuming that this particular true posterior can be approximated by this particular q theta. Okay, so this is suppose the true distribution. So this is the true posterior. So this is the true posterior. And in many cases, basically this true posterior is unknown to us. We can actually identify it up to a certain point. Okay, up to a certain point. It is not possible for go for the true posterior. What you have to do that you are basically doing the simulation and trying to reach to the stochastic is basically change over time with probabilities. Yes, so time nature of the data is getting yes. So that randomness will always be there. But the thing is that in conventional randomness, we are generally calling this particular cross-sectional data. Okay, that we are assuming that all the data points are captured, okay, at the same point of time or almost same point of time. Okay, and in time series data, basically what happens that the dynamicity of the data is being captured, and that is going to give you a better you can say interpretation of the and better prediction of the future. Okay, so now coming to this optimization based method, and these are known as discrete these are known as deterministic approximation. Deterministic approximation. Okay, and in this we are having this particular variational inference and its family. Variational inference and family. Okay, so we are having true posterior and we are having this approximate posterior or representative. Okay, so what will happen that if I want to reach, so our aim is to bring this particular q theta to reach this particular p theta, right? So what we are doing that we are actually creating a lower bound. Okay, so we are creating a lower bound. I think this was covered in the last session, lower bound computation. Can anybody please confirm that whether it was covered in this last session, this lower bound? And this lower bound is basically, it is a measure of that how far it is from the true posterior, how far the approximate posterior is from the true posterior. Okay, so lower bound, what you have to do, so here if you can look at it, so we are basically trying to push this lower bound. Okay, this is the lower bound actually. Okay, so this is the lower bound. This lower bound will be pushed towards the p theta. That means what you are doing, that you are trying to maximize this lower bound. Okay, so what we do, we actually find out something called as evidence lower bound. Yeah, elbow. Okay, so this is called as evidence lower bound. So what will happen, that you have to basically maximize this elbow. Okay, you have to maximize this evidence lower bound. It is to be maximized. So if you can maximize it, okay, if you can maximize it, then we'll tell that q theta is actually moving towards p theta, means the approximate posterior is moving towards the true posterior. Okay, so this is what variational inference is. Right, now what we are going to do, that we are going to basically derive the you can say we'll be starting with univariate Gaussian data. Okay, and we'll be trying to derive that how to calculate the posteriors, how to calculate this approximate posterior. So how to calculate this approximate posterior, there is a big derivation for that. I'm not going into derivation, I'll be just using that final expression. Okay, I'll be using this final expression, and derivation is also very interesting, that how to actually find out this approximate posterior formula. It is also very interesting, but I am not going into that right now because it is not needed. Okay, so we'll be using this particular final expression. Okay, so we'll be using this particular final expression, right? So first we'll be starting with, and you'll be finding another thing, that this variational inference, okay, whatever the expression of the posteriors we are getting, okay, it is quite same as the this particular Gibbs sampling. Okay, so quite same means almost same. Okay, we'll be having. So basically, if we are assuming, so assuming q theta, okay, approximates p theta, so q will be used for approximate, and p will be used for true one. Okay, so then q star theta, okay, will be given as exponential, okay, expectation of I not equal to j, okay, or we'll be writing it as set difference theta. Okay, so we'll be coming to that. Then log of probability of x, z, and all those random variables divided by this exponential of expectation of I not equal to j. So this will be actually qi theta I. No, so let me reframe this. This notation might be wrong. So let me reframe this. Then I'll be giving you example. Then I think you will be understanding that exactly what do I mean. Okay, so here, yeah. So this is the notation we use. Can anybody tell what is this notation that is used? Suppose I am telling a, this one. Okay, so what is that notation? Can anybody tell? Can anybody tell me that what is this notation about? Can anybody tell me? So this is called as set difference. Okay, this is called as set difference. Means from A, I am not using, I am removing this B, and the rest of the set is actually coming here. So here the notation, basically I can write it as, suppose theta, this is big theta. Okay, if it is considering theta 1, theta 2, okay, dot 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 theta p, then for what are these thetas? Thetas are basically parameters whose posterior I am trying to find out. Okay, so q of theta 1 will be exponential of e of set difference theta. That means we'll be taking all theta 2 to theta p, keeping theta 1 outside. Okay, then log of p x z. Okay, another thing what we can do, that instead of equal to, we can actually write it as proportional to. Okay, so omitting, because in the denominator what is there? In the denominator it will be the evidence. Okay, so we are marginalizing out all the hidden variables. So x is the variables of interest. Okay, z are the hidden variables. Okay, so q theta 1 is proportional to exponential of expectation of set difference theta 1. Okay, so whenever we are finding out the posterior for theta 1, then theta 1 will be differenced. Okay, or you can say theta 1 will be taken out, and rest all the variables will be there. And inside this is the joint probability. Okay, so inside this is the log of joint probability. Okay, so this is what we are going to do. Okay, another thing is basically you will be finding, that is the so this is the optimized posterior. Optimized posterior. Q theta 1. Okay, now another one is the elbow. Okay, so evidence lower bound. So evidence lower bound, actually how it is found found out. So evidence lower bound is basically, you have to look at that what is the expected value of the true posterior, and what is the expected value of the approximate posterior. Okay, so let me just 1 minute. I little bit confused about that particular expression. Elbow. Yeah, elbow will be given as the lower bound for this particular Q will be expected value of ln p all theta, okay, minus expected value of ln all q theta. Okay, now this will be, so here the expectations, how the expectations will be carried out. These expectations will be carried out in terms of the present theta parameters there. So what we are doing, that expected value of the log of true posterior, this is actually true joint distribution. Okay, so that is, yeah, this is okay. This is not a incorrect notation. This is actually correct notation. Okay, so this is the joint distribution. Here this theta is actually theta 1, theta 2, dot dot dot, theta p, all this theta. Okay, so in that way it is given. Now the thing is that so along with this, there will be I have actually missed out that this thing. So this is actually theta comma the data also. Okay, theta comma the data, that joint distribution. So this is the joint distribution. Okay, and this is the approximate posterior distribution. approximate posterior distribution. Okay, so now let me do one thing. So now we'll be going into this particular derivation of a particular situation. So we'll be talking about univariate Gaussian first. Okay, so we'll be talking about univariate Gaussian first, and we'll be trying to see that how this is getting derived. Okay, so was it shown in the last session? Can anybody confirm me? Can anybody confirm that was it shown in the last session, that how to derive these particular posteriors for different because tomorrow the first session will be on sparsity in variational linear as well as logistic regression. So there I'll be taking that session, and I'll be talking about more detailed into that. Suppose you are having these conjugate priors and all these things, right? Now you are having sparsity in your data. Okay, what is that sparsity? That there will be many zeros and very few ones. Okay, or very few non-zeros. Okay, so many zeros will be there. So that means what will happen, that matrix, the design matrix might not be very good to work with. Okay, what will happen, that if you calculate the inverse, so whenever you are doing this particular linear regression or any kind of regression problems you are doing, then definitely this particular uh, inverse, finding out inverse problem will be there. Okay, so you have already seen that in linear regression basically we are trying to find out the inverse of xt, some kind of inverse actually we are finding out, x transpose x, right? So for SLR and MLR you have already found out. Okay, now the thing is that if the data is sparse data, that means the predicted data set is containing too many zeros, then what will happen, that this particular matrix will not be a stable, the inverse of this particular matrix will not be a stable one, it will be inconsistent one. So what we have to do, that we have to find out some kind of method which can actually give us a stable stable prediction. Okay, stable estimate of the parameters and stable estimation. So it should not change, it should be consistent. Now the thing is that how to do that, how to actually solve that kind of problem in real data set, that we have a different types of, you can say variable selection problem. Okay, so we'll be talking at length in tomorrow's session. So variable selection problem. In variable selection problem, basically what we are doing, that we are actually assuming that not all the predictor variables are equally important or equally significant. Okay, very few among the many of the predictor variables, very few are actually, you can say, significant. Okay, very few are significant. So we are actually having this kind of biased, you can say we are having that. This is why this bias is given in the system. Okay, this is how the bias is given in the system. So yesterday I was telling you that statistics is, in many cases we are actually intentionally inputting some kind of bias in our prediction and interpretation, and that actually helps us in some ways. Okay, now first is that we are going to look at something called as univariate Gaussian. So univariate Gaussian. So what we are going to do here, that suppose I have got a data set which is following normal distribution, and I have to find out where is its mean and where is its variance. Okay, so objective is to find out the mean and variance of a data set, assuming the data follows normal distribution. Okay, so if the data follows normal distribution, then it will be having the likelihood. Okay, the likelihood will be having likelihood will be given by the normal distribution. Okay, so T is the data, mu is the mean, and tau is the precision. I'll be taking tau because it will be having little it will be little easier for us to work with tau. Okay, so this is tau. Tau is the precision. So the likelihood that will be given by P of D given mu and tau. Okay, so this will be likelihood. Is it okay? Now likelihood will be, how to calculate this likelihood? So likelihood will be given as, it will be given as, suppose that will be product of I equals to 1 to n, whatever we did in the last class, yesterday's thing. Okay, so you can remember. So this will be under root 2 pi, okay, multiplied by tau to the power half. So why it is tau to the power half? Can anybody tell? It was 1 by under root 2 pi sigma square, right? So sigma square is tau inverse right now. Okay, so sigma square is tau inverse right now. So sigma square, if it is tau inverse, so tau is sigma square inverse. Okay, so it was 1 by under root 2 pi sigma square. So sigma square, if you replace it using tau, then in the denominator it is becoming tau to the power minus 1. Okay, tau to the power minus 1 and square root of that. So tau is going in the numerator and it is becoming tau to the power half. Is it okay? Now this will be exponential minus tau by 2, and the data variable, random variable, I am assuming as xn, x. So xi comma xi minus mu whole square. So this is what is the likelihood. Okay, so log of p d mu tau will be n by 2 minus n by 2 log of 2 pi, n by 2 minus log of 2 pi, sorry, minus n by 2 log of 2 pi. Then yeah, sigma 2 has been replaced. So sigma square is actually tau inverse. So that's why tau is called as precision. Okay, that's why tau is called as precision. Because it will be having little bit easier calculation. Okay, so we'll be saying yesterday we did gamma, inverse gamma distribution. Na? So today let me show you what is gamma distribution. So gamma and inverse gamma, they are just reciprocal to each other. Okay, gamma and inverse gamma, they are actually reciprocal to each other. Okay, so the log of P of D given mu comma T tau is minus n by 2 log of 2 pi, then plus n by 2 log of tau. Okay, plus n by 2 log of tau minus minus summation of so tau by 2 will be coming out minus summation of xi minus mu whole square. And this xi minus mu, actually we can write it as x minus mu transpose multiplied by x minus mu. Okay, so minus n by 2 log of 2 pi plus n by 2 log of tau minus tau by 2 x minus mu transpose x minus mu. You can write it like this. Acha. Now next is that I'll be assuming that what is the probability distribution of this mu given tau. Okay, so why it is actually conditional, the mean, why it is getting conditional on the precision, it is having a reason. Okay, so if you don't generally don't condition it on the if you don't condition it on the precision, then generally what happens is the estimate of this mu gets fluctuating. Okay, inconsistent estimation. So that's why we go for this particular mu given precision. or mean given precision. So now we are assuming it as normal distribution. Okay, mu of mu naught, comma, lambda naught and tau inverse. Okay. So as tau is precision, so it is inverse I'm taking, and lambda naught also I'm taking as precision of the mu. Okay. So that's why this particular lambda naught is also inverse coming. Okay. So this will be having my PDF as minus. So now I am telling that what is the dimension of this particular, is it a multivariate case or is it a single univariate case? So I have taken univariate case. So it will be coming as my n by sorry, this will be 1 divided by 2 pi, and in the numerator it will be lambda naught tau, okay, multiplied by exponential of minus lambda naught tau by 2, and this will be mu minus mu naught whole square. Okay, so now log of p mu given tau is actually coming as half log minus half log 2 pi, okay, then plus log of lambda naught tau, okay, plus sorry, minus summation minus lambda naught tau by 2 summation of, so summation is not required because this is univariate, so take a summation nahi chahiye, so summation is not required. So this will be mu minus mu naught whole square. Acha, next is the p of tau. P of tau is assumed to be gamma. Okay, so it is assumed to be gamma distribution of tau given a naught b naught. Okay, and this will be, can anybody tell me what will be the PDF of this gamma? Yesterday what did you do? What did we do? So it will be, it was b naught to the power minus a naught minus 1 divided by gamma function of, it was gamma function of this particular a naught, okay, and then multiplied by exponential of minus b naught by x it was. So let me just cross check that whether I am correct or not. So gamma distribution, so in Wikipedia and it's all available, this distributional forms. Okay, so gamma distribution, yes. So now gamma distribution is, so gamma distribution is, I'm forgetting. Okay, so this will be b naught to the power a naught minus 1 by gamma a naught. Okay, multiplied by then multiplied by to the power exponential. Achha, let me check that yesterday what did I do. Just 1 minute. Let me verify yesterday's slide. Gamma inverse gamma distribution was inverse gamma. It was sigma square to the power minus gamma minus 1 divided by exponential minus delta by sigma square. Okay, take it. So here it will be. So if it is gamma distribution, then it will be, I can actually remove this particular gamma function in the denominator. Okay, what happened? Okay. Just 1 minute. You cannot write. Huh. So this is. I cannot erase also. So I'm crossing it. Sorry, I'm cutting it. Okay. So P of tau will be gamma of tau given A naught B naught. Okay, so that will be written as B to the power B naught to the power A naught. Okay, then tau to the power A naught minus 1 and exponential minus B naught tau. Okay, so this is the expression for gamma distribution, right? Now the thing is, what now my stage is set. Okay, so I want to find out, my intention is to find out what is the posterior on, so what is the posterior I want to find out. So P of mu comma T I want to find out, and that is coming as mu comma T given D. That is the posterior I want to find out. So mu T given D. Okay, so this will be D given mu comma T, P of mu given T. Okay, so this will be P of mu given T and P of T divided by something. Okay, so this will be proportional to. This will be proportional to. So let me write it. So P of mu comma T given D will be proportional to P of P given mu comma T multiplied by P of mu given T, mu given tau multiplied by P of tau. Okay, now this is the posterior I want to find out. Okay, this is the posterior I want to find out. But I am basically I cannot find out the exact true posterior. Okay, so we are doing approximation using Q mu tau. Okay, and this Q mu tau will be taken as Q mu multiplied by Q tau, and this is called as mean field approximation. So this mean field approximation, I think it was mentioned and it was explained in the last class. Was it explained there? Was it explained there? Can anybody please confirm me? Okay. So, so we are actually factorizing the joint posterior, okay, as the individual posteriors. Okay. So now, following the optimized variational distribution formula, okay, we are getting ln q star of mu. Okay, now as it is a function of mu, so the expectation will be taken on all other parameters except mu. It will be taken on all other parameters except mu, and in on what this expectation will be taken, that will be the joint distribution. So data mu and tau. Okay, this is how it is coming. So when I am interested in finding out the posterior for mu, the expectation will be taken with reference to parameters except mu. Now, what is the other parameter here? That is tau. So the expectation will be based on tau. Okay. So here the theta is mu and tau. So whenever it is except mu, then it is tau, and whenever it is tau except tau, then it is actually with respect to mu. Okay, so in this way basically we are doing. Now inside bracket, how to expand that? So this is a joint distribution. So joint distribution will be expanded like this. Okay, so it will be P of D given mu tau plus log of P of mu given tau plus log of P of tau. Is it okay? Now the thing is that from these three components, one component will not come. Why? I have to look at this particular, for what variable I am going to find out the posterior, that is mu. So I have to find out that which of the probability distribution that is a function of mu. If it is not function of mu, then we'll be removing that, we'll be omitting that. So here this P of tau, it is not involving mu, so we'll be removing this. Okay, we'll be ignoring this. Okay, so now it will be constant. It will be constant. So expectation except mu. Okay, so this will be ln p, this one tau plus mu ln p of mu given tau. Okay, so now on what variable this particular expectation will be calculated? With respect to tau, it will be calculated. So E of tau, okay, so E of tau. So what is this ln p d given mu comma tau? That is coming from this slide. Okay, so we can write it in this way. So minus n by 2 log 2 pi, then plus n are you following me? So then n by 2 log of tau. Sorry, what is that? Tau, log tau. Okay, then we are having minus tau by 2. So this will be minus tau by 2 summation of x I minus mu whole square. Okay, so this is what it is coming. Okay, and then plus expected value with respect to tau. Okay, that this one. So now this is coming as log of lambda naught tau. Okay, log of lambda naught tau. Then lambda naught tau by 2. Then it is minus lambda naught tau by 2 mu minus mu naught whole square. Okay, now here is another point. So this particular function does not contain mu, so ignore. This function does not contain mu, that is also ignored. This function also does not contain the mu, so that is also ignored. Okay, so let me write it somewhere. So does not contain mu, so ignore. This will be actually ignoring means they are going into these are the part of constant. Okay, so part of constant. So I think it will be better not to write it as 0. So let me just rewrite it. Okay, so part sorry. Part of constant. So this is part of constant. Okay, so this is also constant. This is also constant. This is also constant. Okay, so what is remaining now? So this will be E of tau of, acha, change the color. So E of tau of, okay, so first one is minus tau by 2 summation of xi minus mu whole square, and then it is lambda naught by tau by 2, okay, mu minus mu naught whole square. Okay, so now tau you can take out, but what will happen that it will be acha. So the expectation is with respect to tau. Okay, so this will be E of tau by 2 minus, okay, then it will be summation of xi minus mu whole square minus of so minus has gone out minus yeah, plus mu minus mu naught whole square into lambda naught. Okay, now you can actually uh, make it a little bit you can say you can do refinement of this particular expression, and you can actually find out in terms of mu what is the mean and what is the variance. Okay, so it will be coming as minus E of tau by 2, okay, and then summation of xi minus mu whole square plus mu lambda naught into mu minus mu naught whole square. Okay, done. Achha, now this will be I equals to 1 to n. So this will be E of tau by 2. Okay, E of tau by 2. Then it will be summation of xi square minus 2 xi mu plus mu square. Okay, then plus lambda naught mu square minus 2 mu naught plus mu naught square. Okay, so minus E of tau by 2. Okay, then summation of xi square not needed. Now 2 into mu into xi, that is actually needed. Okay, then mu square. So here it will be summation of mu square. What it will give? It will be summation of 1, that is the number of observations. Okay, so it will be n mu square minus 2 into mu into summation of xi. Okay, here acha. In this case there also this particular mu naught square will not be required because this is a constant, it does not contain mu. So this will be lambda naught mu square plus sorry minus 2 mu lambda naught mu naught. Okay, now collect the mu square terms. Okay, so this one is this one, minus E of tau by 2, then it is becoming n plus lambda naught mu square minus 2 into mu into summation of xi plus lambda naught mu naught. Okay, so this will be inside. So now minus E tau by 2. Now take this n plus lambda naught outside, so n plus lambda naught. Now this is mu square minus 2 into mu into summation of xi minus lambda naught plus lambda naught mu naught divided by n plus lambda naught. So this is the mean part. Okay, plus constant. So this will be plus constant plus constant plus constant like this. So plus constant like this. So here, so this is a normal distribution. Okay, so normal distribution, what is its mean and what is its variance? So variance is n plus lambda naught inverse, and mean is summation of xi plus lambda naught mu naught by n plus lambda naught, in that way. So this is actually nothing but along with this you are having minus et by 2. Okay, you are having this one, right? So in this way you can actually find out that what is the so it will be coming in the variance. Okay, this will be coming in the variance, right? So this is going to give you this particular variational approximation. Okay, it will be giving you the variational approximation of this particular univariate Gaussian. So you can find out that what will be its mean and what will be its variance. Okay, so the mean will be the mean will be x bar plus lambda naught mu naught by lambda naught plus n. Okay, so how it is coming? This is actually coming as have I done anything wrong here? Any mistake? No, it's correct. So lambda naught mu naught plus n x bar. Yeah, n x bar. This will be n x bar. Okay, how it is coming as n x bar? So x bar equals to summation of xi by n. So summation of xi equals to n x bar. Okay. Achha, now what is the variance? So variance is, I am taking that variance is, so variance I had considered lambda naught. Okay, so this is I am considering as lambda n. So this will be lambda naught plus n multiplied by e of tau. Sorry, this lambda n is not variance, it is the precision. Okay, so this is why we are actually considering precision instead of variance while doing this Bayesian calculation. So this is so mu follows a normal distribution. So Q of mu is normal distribution with mu n and lambda n. Is it okay? So in this way it is derived. Next is that I'm going for so any doubt till now what we are doing actually? Any doubt till now? Now we are going to this particular deriving this Q of tau. So similarly, ln Q star of tau, okay, Q star of tau will be E of difference tau, okay, means except tau, we are having ln P data given mu t plus ln P of mu given tau plus ln P of tau. Now, in the first step, okay, so I'm not going to ignore any kind of distribution. Why? Because all are actually dependent upon tau. All are actually dependent upon tau. So we cannot remove that. Okay, so first of all, it will be expectation will be in terms of mu. Okay, means mu and tau, two parameters are there. So if I am taking set difference of tau, that means we are having only mu. Okay, so this will be so I'm straight cut. I am writing out the final expression. So should I go by step or should I do some kind of step jump? Can anybody please confirm? So this will be containing n by 2 log tau minus tau by 2 summation of xi minus mu whole square. Okay, then plus I'm ignoring this n by 2 log pi and all these things, log 2 pi and all these things. Achha, then it is lambda naught tau. Okay, then it is lambda naught tau mu minus mu naught square. So this is actually lambda naught tau by 2, okay, mu minus mu naught whole square. Achha, here one thing I didn't tell you, that what is this particular expected value of tau. So tau is following gamma, okay, distribution, right? Now what will happen, that we have to find out the parameter an, okay, an bn. Instead of a naught b naught, we'll be starting with a naught b naught, we'll be just updating it step by step. So a naught b naught will be coming, a and bn will be coming in the next step, whereas this mu n and lambda n, they will be coming in this step, and that will be used here as well as in the next step. So I'll be telling you that I'll be explaining you that how this is actually happening. Okay, so n by 2 ln tau minus tau by 2 summation of xi minus mu whole square. So next is lambda naught tau by 2. Okay, this will be just 1 second, mu by tau log of lambda naught tau. Okay, so log of lambda naught tau will be giving you only log of lambda, log of tau. Okay, because it is coming outside, log of lambda naught will be coming outside. So this will be ln tau, half ln tau, okay, plus minus lambda naught tau by 2 mu minus mu naught square. Okay, then it will be coming as then the gamma distribution. So gamma distribution, actually what is the form here? Where did I write gamma? Gamma is coming as b naught to the power a naught, right? So this will be a naught log b naught, not required because it is not dependent upon tau. So it will be coming, it will be ignored. So here it will be a naught minus 1 log tau plus minus minus b naught tau. So it will be plus a naught minus 1 log tau minus b naught tau. Okay, so this is what the total expression. This is the total expression. Now all these components which are not having mu here, they'll be coming out as it is because they are constant in terms of the expectation with respect to mu. So this will be n by 2 ln tau, okay, then half ln tau, okay, that will plus a naught minus 1 ln tau, okay, they have all come out because they are not depending upon tau. Okay, then rest of the things that are actually we have to find out that this b naught tau, okay, then this lambda naught tau by 2, mu minus mu whole mu naught whole square, as well as this one minus tau by 2. So we have to actually look at this. Okay, so here it is coming as minus b naught tau. Okay, so let us do one thing, take the tau outside and then we will complete. So minus tau multiplied by b naught. Okay, then minus tau by 2 summation of xi minus mu whole square, then minus lambda naught by 2 mu minus mu naught whole square. And this will be actually, it is having expectation of this mu will be working on this. Now where it will be working? It will be working only on this part. Okay, because it is having only these components are having mu in it. Okay, so that's why. So let me just write it little clearly. So this is tau by 2, no, not 2. So this is tau b naught minus, okay, expectation of this particular quantity with respect to mu. Is it okay? Is it okay? Anybody is following this? Okay, now let us look at this particular. Now let us look at this particular. Yeah, it is correct. So let us look at this particular. So now let us club or collect the terms which are containing ln tau and tau. Okay, so ln tau, if we are collecting this, so a naught plus n by 2, okay, and then n by 2, and then here I think I have done some mistake in this is plus, yeah, so this will be n by 2 minus half, okay, minus half. So minus half, instead of minus half I am taking plus half, okay, here, and minus 1. Take it. So a naught plus n by 2 plus 1 by 2. Okay, now minus tau b naught minus this part. Okay, so e of this part summation of xi minus mu whole square minus lambda naught by 2 mu minus mu naught whole square. Okay, so now this is actually coming in terms of gamma distribution only. So gamma distribution actually, if you look at this, so p of tau given a naught comma b naught, it is actually coming as b naught to the power a naught minus 1. Okay, so that is not required. So tau to the power, it is coming as tau to the power a naught minus 1 and exponential minus b naught tau. Okay, so if we take log on both of these sides, so log of p of tau given a naught comma b naught, that will be a naught minus 1 multiplied by log of tau minus b naught tau. Okay, minus b naught tau, right? So here what is happening, that here I think I have done a mistake, that here it will be 2 was there, half. So it was half here, and this will be plus, this will also be plus, this will be half. Okay, now the thing is that this will be, and this will also be plus, this will also be plus. So instead of a naught, instead of A naught, I am getting A naught plus N plus 1 by 2. And instead of B naught, I am getting B naught plus this one. Okay, so this is what actually happening, right? So I am writing it as AN, that is the parameter of the this one. So we are telling Q star tau is gamma AN BN. Okay, and AN is A naught plus N plus 1 by 2. Okay, because I have to keep this -1 also, so this -1 is intact. I am not disturbing it. And second one is that B naught has become Bn. So Bn is B naught plus expected value expectation over these particular two terms. So this will be half, okay, and summation of xi minus mu whole square plus lambda naught mu minus mu naught whole square. Okay, and the expectation is with respect to mu. So in this way, basically, this is the derivation. Okay, now implementation, you'll be seeing that this is very, very easy. So basically, uh, how that loop will be working. Okay, so how that this particular variational algorithm will be working here. That so the algorithm is start with any mu naught tau, then lambda naught, A naught, B naught. Okay. Now, what are the things you know? You know this X data, you know number of data points. Okay. And these two are actually more than enough. Okay. So here what will happen that mu will be replaced by, okay, mu will be replaced by n x bar plus lambda naught mu naught divided by lambda naught plus n. Okay, so mu will be replaced by n x bar lambda naught mu naught divided by n plus 1, n plus lambda naught, sorry, n plus lambda naught. Then tau will be replaced by lambda naught plus n multiplied by e of tau. Okay, then a naught will be replaced by a naught plus n plus 1 by 2, and b naught will be replaced by b naught plus half e of expected value of this whole term. Now, how this expectation is calculated? So I'm going to show you very quickly. Okay, so here, so this will be running in iteration. So this is for suppose 1000 iteration, I equals to 1 to 1000, right? And based on this, you can actually calculate the elbow also. Okay, so you can actually do this step by step. Acha, what kind of variational inference this is? This is known as CAVI. I think it was mentioned in the earlier class. Okay, coordinate ascent variational inference. Okay, so coordinate ascent variational inference, CAVI. What you are doing? First, I am updating mu, then tau, then A naught, then B naught. Again, then going back to mu, then tau, then A naught, then B naught. In this way, we'll be running these iterations in for suppose 1000 times. Then you'll be seeing that after a certain point of time, it is getting stabilized. Now, variation. What is the advantage of variational inference? Variational inference is very, very fast. It's very fast. Very fast means very fast. Actually, if you go for this Markov chain Monte Carlo, then suppose to create 10,000 samples, if you take around 2 minutes time, this will be hardly taking 1 or 2 seconds, okay, for the same data. So this is how actually this is very fast, this variational inference. Now one downside of variation, any downside of variational inference, can anybody tell? I think it was discussed in the last class. Any downside? So Markov chain Monte Carlo based kind of simulation or Hamiltonian Monte Carlo, they are actually very, you can say, costly. It will take too much time, computational resources also. But variational inference is very fast. Okay, I want first interpretation, first inference, okay, or first fast, you can say, prediction. But the problem is that it actually underestimates it is actually working in expectation finding framework. You can find it out. Okay, expectation finding framework. Why? Because everywhere we are actually trying to find out expected value. Okay, so here it is underestimating the variance of the prediction. Is underestimating the variance of the prediction. So basically, so let me write down the comparison of sampling and comparison of sampling and variational inference. Okay, so sampling and VI. Okay, so first one is that sampling is okay. First, I am writing strengths. Okay, strengths are sampling is basically, you can say, it is consistent prediction. Consistent prediction if used for based settings. Second one is that approximates the true posterior in based form. Okay, now come to drawbacks. It requires diagnostic tests. It requires diagnostic tests. Okay, so what are these diagnostic tests? That is basically autocorrelation, if it is happening or not. Okay, especially this one, right? Yesterday I was telling that the first iterations, okay, first suppose 1000 or 2000 iterations, they'll be having these particular autocorrelations. Okay, so you have to remove that or those samples, which is named as burn-in. Okay, there are many other kind of diagnostic tests are there. Next is find out, okay, ESS, effective sample size. Effective sample size. This is also very important. Okay, so that's why these are the drawbacks of sampling framework. Now, strengths of variational inference. It is super fast as compared to sampling. Okay, second one is massive parallelization. Which is not possible in case of, which is possible, but the thing is that it will be creating some kind of cross correlation also. Okay, so here in variational inference, no cross correlation, no auto correlation. Okay, next is anything else. So it will be requiring much lesser computational resources as well as storage resources. Okay, but now coming to drawbacks. Always talks about expectation, variance of posterior is underestimated. So this is the problem. Okay, so this is the comparison of sampling and variational inference. Okay, so let us now move to this particular variational inference for linear regression. Now I am not going to solve it step by step. I am not going to show you step by step how I am arriving at. I'll be doing little bit step jumps. Okay, so variational linear regression. Okay, so here what I am going to do, that I am going to have the model like y equals to wx, okay, plus epsilon. Okay, so instead of beta I am writing w. Okay, let me write beta itself. Okay. Beta x plus epsilon, and beta might be multi-dimensional. So it is actually x beta. Okay, so n cross 1, then n cross p, then p cross 1, then n cross 1. Okay, now the hierarchical structure, hierarchical model, okay, hierarchical model is written, means that structure of that regression, okay, written as p of y given w. Okay, that means this is the likelihood. Okay, so this is, I'm assuming that it is following a normal distribution, I equals to 1 to n, normal distributed yi given w, beta x, comma rho inverse. Okay, so what is this rho inverse? Rho inverse is basically the precision. Okay, rho is the precision of the error. Okay, so this is the likelihood. Then we are having p of w given alpha. I'm taking what's a w, to change w, beta. So beta given alpha. So I'm taking it as normally distributed. Okay, w mean is 0 and precision is alpha. Okay, alpha inverse I. Okay, I, why I am taking that, this beta is basically a multivariate situation. Again I am writing w, it will be all beta. Okay, and p of alpha is gamma of alpha a naught b naught. Okay, so the joint distribution will be p of y w alpha. Okay, while y beta alpha, and it will be p of y given beta multiplied by p of beta given alpha, and then p of alpha. This is the structure. Okay, now rho also you can take. Okay, so rho, I'm assuming that it is known to us. Okay, otherwise you can take that also. Okay, you can actually have that hierarchy also. So here what would have happened, that if, so here rho is known. So had it been rho unknown, okay, had the rho been unknown, so then it would have been p of y given beta rho. Okay, that will be the likelihood. P of beta given alpha and rho, and then P of alpha. Okay, and then P of rho also. Okay, it would have been. So it would have been. Okay, so if rho was unknown, rho unknown case. Okay, rho unknown case. Now I'm assuming that rho is known to us. So here the variational distribution is taken as variational distribution is taken as Q of beta and alpha. These are the parameters I want to estimate. Okay, that simulate. So it is assumed to be Q beta, Q alpha. Okay, so now first we are going for Q alpha. So ln Q alpha will be equals to ln. So it will be so here it will be expectation will be with respect to all the parameters except alpha. So it will be written as expectation minus alpha. I am taking. Okay, I'm writing in a different way. Okay, minus alpha. You can write set difference also. No issues. So this will be ln p y given beta plus ln p of beta given alpha plus ln p of alpha. Now here in the first part there is no alpha. Okay, so we can actually ignore this constant. Okay, remove this. So now this will be ln p of alpha. Okay, because ln p of alpha, why it is coming out? Because the expectation is with respect to the parameters, with all parameters except alpha. Okay, except alpha. So this will be, so ln p alpha is coming as it is outside. So plus this will be e of beta. Okay, and within bracket it will be on what quantity we are getting the expectation, that will be p of beta given alpha. Okay, now what is the p alpha? Actually p alpha is gamma distributed a naught b naught, right? So a naught b naught, it is so if I take ln, so ln, this will be ln, this will be a naught minus 1 ln alpha minus b naught alpha. Okay, so this is becoming a naught minus alpha ln alpha minus b naught alpha. Then suppose the beta is m dimensional. So suppose beta is m dimensional. So beta given alpha, I have to take, what is beta given alpha? Beta given alpha is normal distributed with mean 0 and precision is alpha variance is alpha to the power minus 1 I. Okay, so we'll be writing it as plus m by 2 ln alpha minus alpha by 2 expectation of W transpose W. Okay, and with respect to W. Here is a trick actually we have to use. Okay, later we'll be doing that. So this is, you can see that it is coming as ln alpha. If you club, then you'll be finding a naught plus m by 2. Okay, minus 1 ln alpha plus, okay, now alpha term if you club, then you'll be finding minus, then alpha into b naught plus half into expectation of W transpose W, okay, with respect to W. So this is coming as a gamma distribution. So Q star alpha is coming as gamma distribution with an and bn parameters, and an is a naught plus m by 2, and bn is b naught plus half expectation of, sorry, this one is beta transpose beta with respect to beta. Yes. Here, inside it will be beta transpose beta, and it will be with respect to beta. Okay, beta transpose beta, and here also beta transpose beta, and this is b. This is beta. Okay. So next is that how to actually find out this. Can anybody tell me how to find out this expectation of beta transpose beta with respect to beta? Can anybody tell? Where from it is coming? You can actually use an identity to find out that what is the expected value of beta transpose beta, or suppose x transpose x. Okay, expectation of x transpose x with respect to x, if you want to find out. Then how to actually find out? We can actually use this particular Vx equals to e of x square minus e of x whole square. This particular identity we can use. So if I want to find out e of x square, so this is becoming v of x plus e of x whole square. Okay, and yeah, beta 2 means beta square kind of, if you want to find out. So beta square is nothing but beta transpose beta. So that's why we can use that. Okay, so in that way. So this is a very cool trick. Okay, you can have and you can actually find it out. So this will be beta naught plus half. Now this is actually beta transpose beta. So for beta transpose beta, it is coming as we can find it as so here it is e of x whole square, right? So e of x, if it is suppose mu, then it will be mu square. Now mu square actually it is if you want to write in terms of vectorized form, then it will be mu transpose mu. Okay, so we'll be getting this particular mu n. Mu n will be getting for the normal distribution. The next derivation we can find out, plus then Vx. So Vx is basically the variance covariance matrix in case of this multi-dimension. So, but this Bn is a scalar quantity. So now you see that mu n transpose mu n, that is also a scalar quantity. So Vx instead of Vx will be having a variance covariance matrix. So we have to take trace of that variance covariance matrix. Okay, so we will be coming to that, deriving mu n and Sn in the next step. Is it okay? So this is for alpha. Okay, so this is for alpha. Now we are coming to this particular, find out that what are the parameters for W. Okay, and that will be coming in almost same way. So Q star W will be expectation of ln P, sorry, not W, it is beta. So this is beta. So P of beta, sorry. First one is P of y given beta plus ln P of beta given alpha plus ln P of alpha. Okay, so this is the joint distribution. So we'll be always starting with the joint distribution. Okay, so we'll be always starting with the joint distribution. Now, this ln P of alpha, it does not contain beta, so we can ignore this. Okay, this is a constant. And the expectation will be with respect to all parameters except beta. Now, except beta, what is the parameter here? That is alpha. So, E of expectation of this one with respect to alpha. So, expectation of, so first one is minus, so m by 2 log of, so m by 2 ln alpha. So m by 2 ln alpha minus alpha by 2 w transpose w. Sorry, beta transpose beta. Sorry, still it is in w in my mind. Beta transpose beta plus ln p of beta given alpha. So this will be, achha, 1 minute. I'm doing this thing wrong. Okay, so this will be minus beta by 2, okay, minus beta by 2 summation of xi, sorry, yi minus xi beta. What is the precision here? Precision I have to bring. Precision क्या था? Precision था rho. Oh, sorry, this will be rho by 2, then summation of yi minus xi beta square. Okay, and the other rho term that will not be required because it is not dependent upon beta or alpha, so gone. Okay, plus m by 2 ln alpha, m by 2 m by 2 ln alpha. Okay, that will also be ignored. So this will also be ignored, minus alpha by 2. Okay, then the beta transpose beta from the last one. Okay, so now we are coming to this particular. So now we are coming to this particular. So here it does not depend on alpha. Okay, so it will be coming as it is. Alpha rho by 2 summation of yi minus xi beta square. Okay, minus, now here it is having this alpha, so it will be p of alpha by 2 beta transpose beta. Okay, beta transpose beta. Now we'll be expanding this. So this will be minus rho by 2, and I am writing it as y minus x beta transpose. So y minus x beta transpose y minus x beta minus e of alpha by 2 beta transpose beta. Okay, so minus rho by 2. So this will be coming as y transpose y. I am removing, I am ignoring. So this will be beta transpose x, then beta, as we were doing yesterday for give sampling. The same kind of thing will be coming here also. Then minus 2 beta transpose x transpose y. Okay, plus beta transpose beta multiplied by e of alpha. Okay, expectation of alpha. So this is becoming minus rho by 2. Okay, so here beta transpose x transpose x plus e of alpha, then beta Okay, then minus 2 beta transpose X transpose Y. Okay, and then X transpose X plus E of alpha I am taking out. Okay, so minus alpha rho by 2 X transpose X plus E of alpha X transpose X plus E of alpha. I am taking it out. So this is becoming beta transpose beta minus 2 beta transpose X transpose Y multiplied by X transpose X plus E of alpha inverse. Okay, so in this way. So this is the new mean right now. So mu n will be mu n will be uh, mu n will be rho rho multiplied by X transpose Y multiplied by X transpose X plus E of alpha inverse. Okay, and the new covariance matrix will be X transpose X plus E of alpha inverse. Okay, so this is the parameters of Q beta star. Okay, now what is the E alpha, by the way? What is E alpha? Alpha is actually following gamma distribution, and for gamma distribution, what is the expected value of alpha? Expectation of alpha is actually expectation is En by An by Bn, A by B. Okay, so expectation of alpha equals to An by Bn. So An by Bn will be A0 plus M by 2 divided by B0 plus B0 plus half E of beta of, we have already done that also. So this will be half of mu n transpose mu n plus trace of Sn. Now this mu n and Sn you can find out from here. So now it will be uh, revolving into iterations. Okay, means coordinate ascent variational inference. So this is what the how this particular variational inference is implemented for linear regression. Is it okay? So I want to take around 10 minutes break. After that, we'll be starting once again, and we'll be going for logistic regression, and then we'll be going for implementation this using Python. Is it okay? I want to take 10 minutes break, 10 or 15 minutes. Okay. Then we'll be going for logistic regression, and then we'll be, so logistic regression is having little bit trick, because if you use normal distribution as a prior on the beta, likelihood is Bernoulli. If you have normal distribution on the beta, that means the coefficients. So beta and normal distribution and Bernoulli distribution, they are actually they don't come into this conjugacy. Okay, so posterior you cannot find it in the same way. So what you have to do, you have to basically make some kind of approximation, which is called as local variational approximation in case of variational inference. Yesterday we saw that we can actually use Metropolis Hastings inside Gibbs sampling. Okay, so here what we will be going to do, that will be doing some kind of local variational approximation, and based on that approximation we'll be trying to find out that what is the posterior that is coming. And I'll not be going to derive many things. Okay, it requires some kind of derivation. I will be writing the final results for this local variational expression. Okay, so I'll be meeting after 15 minutes. Okay, so at 4:40 I'll be starting once again. So till then you please have a break. I think it is going a little heavy, but this is what Bayesian simulation is. Derivations are difficult, but implementation is very easy. Okay, yeah. Yeah, it will be little bit more heavy. It will be heavy.